Okay, this is a beautiful, I would say, a perfect level exam problem. Absolutely perfect. You haven't seen anything like it, but you basically, even though you don't think you know how to do it. Okay? It's not, it kind of has a little bit of everything. It doesn't quite have torque. Why does it not have torque? Because the ideal pulley. Ideal means massless. Ideal, massless, light. If they don't give you the mass of the pulley, it's massless, or you ignore its mass, okay? So let's look at a block of 100 kilograms is attached to another block of mass M, or the pulley weight is 10. The 100 kilogram block takes 3 seconds to hit the floor, as this is 1 meter below, after being released from rest. Whoa, what is the mass M? You say, what? Okay, if one of them makes you go, what? That means it's covering multiple areas of the class in one problem. Okay, that's what that means. So I gotta think first. What is the mass of? So if we want the mass of M, clearly it's something about the tension, right? And how fast is it accelerating? But we were getting all this weird kinematic stuff. What's going on there? The 100 kilogram block takes 3 seconds to reach the floor at distance 1 meter below. If you dropped a block, a meter, would it take 3 seconds? No. Does that take 3 seconds? No. That seems a little slow to me. So maybe the idea is we get the acceleration of the system from that information, and then we apply that to the system to get M. Oh, it's like a reverse Atwood machine. It's like a Utah machine. So let's draw it. Thank you. Let's see. So use kinematics to get A, the acceleration of the system. And it's just 1D kinematics, so you got to know your 1D kinematics. We have acceleration over a certain amount of time, and we have a distance. It's just screaming. Well, forget it. You don't know kinematics. X equals x initial plus v initial t plus 1/2 at squared. Is that one? Yes. If you're given a distance, it's got to be that one. Well, it could be the vf squared equals vi squared plus 2. What about this? Vf squared equals vi squared plus 2ad. What were we looking for? We're looking for, oh, you can use either one. They gave you so much information. Okay, never mind. Let's go with the first one. But since they gave you a distance, I think you can actually use that one too. So you're full of resources. Okay, so it's going to drop x minus x initial. It's dropping basically a meter. 1 meter equals, so we've already taken this into account. It drops a meter. It had no initial velocity. It was released from rest. So it's really just 1/2 A we're looking for, and then T they gave us, it says it takes 3 seconds to drop a meter. Crazy. Squared. So A is not G here, A is just A. And you get that A is 2/9 meters per second squared. I'm going to answer all these when I get home. Why is there no torque when the pulley is massless? Because it takes no force to accelerate the pulley. It has no mass. So a really light pulley, it'll spin with, if F equals ma, you want to accelerate the pulley. How much does it take? It depends on the mass. So if this goes to 0, then the force you need goes to 0. So you can accelerate something massless very easily. Okay. So somebody asked about the negative sign, so I'm just sort of being cavalier with negative signs on this one. Because all I really wanted was an acceleration. And I'll worry about the negative when we do the more detailed part. It's okay to be cavalier with negative signs if you know what you're doing. So A is 2/9 meters per second squared. If I wanted to come down negative, okay, I would have said then this is the origin and this is the position negative 1 meter. So this is negative 1 meter and this is the origin. So this would have been negative 7. There you go. We did the negatives. We did the negatives. Okay. So now we say we know the acceleration of the system. So now we just do F equals ma on each block. Right now it's just that one sheet. So we know the answer. Right? So the left mass, so the M, and then the 100 kg. Right, so this is now just standard stuff we've done. Tension minus mg equals m times 2/9 in mks units. Right, tension minus mg. Oh no, I'm sorry. Oh yeah, times 2/9 equals ma. And for this one, it's tension minus, I'll go numerical on you there, minus 100 G minus mg 100 equals 100 times 2 ninths, because it's also accelerating, but it's negative because it's down. This one's accelerating up, this one's accelerating down. And then what do we have? We have our favorite thing in the world. 2 equations, 2 unknowns? No, we've actually solved for the tension. If we know the mass is the same, we know it's acceleration, and we know what gravity is, then you actually don't have 2 equations and 2 unknowns here. You solve for the tension. So the tension is 957.8. So not everything is 2 equations and 2 unknowns. Sometimes we just give it to you. If you see 3 equations, 3 unknowns, yeah, we don't need to do that on the exam. All right, and then we say, let's bring that over here. The tension, 957.8 newtons equals this M we're looking for, times 9.8 plus 2 over 9, 2 ninths, 2 plus 9.8 is like 11.9. Oh wait, did I type that wrong? Let's see, now it's G, it's plus, that must be a plus 0.222. So the mass is 95.57. We'll check that algebra. I did these really fast right before. But that's the basic idea. This, when actually you get the tension right away, you take that tension, you plug it in here, you figure out the mass, you get like 96 kilograms. There's part A. How much sooner would the 100 kilograms strike the floor if the cord were suddenly cut? Okay. So this is the Atwood rotational part. It takes 3 seconds. Right? But now, the next part is really just going back to the first week. If we cut the cord, it's week 1. I'm sorry, I can't possibly. We'll never get anywhere. Yeah, no, that one is one out. We'll check it after class. We'll worry about it. But so we cut the cord, then we say, oh, it's going to follow meter. How long to follow meter at full G? 1 meter equals 1/2. Oh, I'm sorry. Minus 1 meter is 1/2 times 9.8 t squared. Oh my God, it can't be negative, but this is also negative. It's going down. And the t is 0.45 seconds. So how do you check that? Well, it had better be smaller than 3 seconds. Okay? If this thing is falling by dragging another mass with it, that should take longer than just falling under gravity. So sure enough, it's 0.45 seconds. So for that part, it's 3 seconds minus 0.45, and the answer is 2.55 seconds. Sooner. If it were in Canvas, I'd try to make it take plus or minus 2.55, but it'll be a human grading it, so they'll get it. Okay, so here now it's a force problem, right? So it was a rotational motion problem, then it was a 1D kinematics problem. Now it's a force problem because we have this crazy flea riding along, right? We got a flea here. So let's read the problem and see if it matters where the flea is. Imagine a flea sits on the face of the pulley near to it. As the pulley turns, it gets harder and harder for it to hold on. Okay, if the flea can at most hold itself stationary on the pulley with a force of 0.1 Newton, will it lose its grip while the mass falls? The flea's mass is 0.1 grams, so you ignore the flea's weight. Okay, so that's it. We're talking about the flea going into rotational motion. V. So the force to spin the flea. What is it? So centripetal motion. AC equals V squared over R. That should be here. The force it takes to create centripetal motion multiplied by M. MAC is the force you need to make something go around this way. Okay. So the biggest force that can be, the biggest, is what? Is 0.1 newtons, did it say? You can hold on to 0.1 newtons. That is impressive. Congratulations. 0.1 newtons. But then anyways, it doesn't depend on where the flea is. Because we thought about rotation around a loop and all this stuff, and it was always about the normal force canceling mg and the critical part. That's because we were considering mg as like work force. Here we can say, what is mg? The force of the weight. The reason they said it's so small, it's 0.1 grams, not kilograms. Did I tell the story about the kilogram? No, not. It's 0.1 grams. It's 10 to the minus 4 kilograms times 9.8, which I believe is 9.8 times 10 to the minus 4 newtons. Okay? So that teeny force, that's very small. That's 10 to the minus 3. That's a millinewton. So this is 0.001 newtons, and this is 1 newton. So they're saying that you ignore this. You don't worry about it. You're just saying the only force that can be applied to the flea and the wheel is that can hold on. Right? The wheel pulls it down at 0.1 newtons. So the question is just, when will it fly off? Will it lose its grip while the 100 kilogram mass falls? Interesting question. So usually in this kind of a problem, you would be solving for the velocity. Right? You'd say, well, how fast does it go for the flea to fall off? But here we want to know, basically really the question is, as this thing falls when it says a meter, does it ever go faster than this? Faster than 0.1 newton equals mv squared over r. Okay, so first probably let's see what I decided to do. Did I solve for v? I basically said, does 1 newton, we compared 1 newton, does 1 newton remain less than mv squared over r? 0.1 newton. That's kind of what we're deciding. Okay? So what I did is said, let's solve this. Let's find that, mv squared over r. Okay? Well, the mass of the flea is 10 to the minus 4 kilograms. R is the radius of the loop. That's why they gave us R. I was wondering why they gave us R. It's 0.1 meters. And then the last thing you need is v squared. Okay. What is v? Let's see. So what is v? Vf is, well, let's see. We know what v is. It accelerates at 2.9 meters per second squared. So it must get to this. Let's see. So I need more boards. Okay. So the fastest v final equals v initial. It starts from rest plus 2/9 meters per second squared times 3. Right. So v final equals 2/3 meters per second. Right. That's vf equals vi plus at. So it gets up to a speed of 2/3 meters per second. But wait, that's the speed of the mass. Oh, but remember the rope, the tangential velocity of the edge of the disk is the same as the rope, is the same as the mass. You actually don't have to go into angular stuff to solve this, right? Because this is the tangential velocity. So we put 2/3 in here, 2/3 squared. So that is the force that will rip the flea off of the disk, right? Or I'm sorry, this is the, let's just solve it. Let me plug it in real quick. What do you get? 4.4 times 10 to the minus 4 newtons. This is the biggest centrifugal force he'll ever need. Okay? Other things at the bottom, he's gonna need 4.4 times 10 to the minus 4 newtons. Does he have it? Yes, his feet can do that. Right? His friction force he can apply up to 0.1 newton. So he's got like 1,000 times the force he needs to stay on the wheel. Okay? Oh yeah, good question. Why does it give us the mass of the flea if it says to ignore it? Question. It depends on what part of the problem you're doing. Right? You ignore it because you don't involve it in the rotational part, but then you need it to solve the comparison of the masses. Yeah, that's rough. That is cruel. That's cruel real world stuff. And then let's see. Show you reason. Flea. Okay. With the same pulley and the same masses, the same initial locations. What must be changed about how the system starts off with a 100 kilogram block to arrive at the ground after 9 seconds. Okay? So think about how, okay, so we said this thing is sitting here, it's a meter above, you drop it, it falls, it goes down, and it takes 3 seconds. That's what we know. How could it take 9 seconds? What could possibly be different? So think about it for a second. Somebody's going to shut up the answer. How could it take 9 seconds? How would you do it? Anybody want to shout out? How would you make this take 9 seconds to get to the ground? Right, you'd throw it up, you'd vomit. You'd vomit on this problem. It might happen. I've seen it happen. You would have to throw up, is what it says. So what you would need is for this to take, you would want to say, okay, I'm going to think it's good to think in terms of a coordinate system here. So if the ground is the origin now, and we're starting here, we want to throw it up like that. And we want to land here in 9 seconds. Okay, 1D kinematics. Y final equals Y initial plus V Y initial T plus 1/2. The acceleration will still be 2/9. It's still hooked up to this whole system. Nothing really changed about the tensions and all that stuff. It's still, that's still all the same. 0.22 or 2/9. And then 9 squared. I've kind of started filling in, sorry. So the final position would be 0 is 1 meter plus we need Vyi times 9 plus 1/2 to 9. Oh, but wait, is it plus or negative? It's a negative at that part, right? It's going down. Minus 1/2 to 9 squared. Set it up like that and solve for Vyi. That's how fast you have to be moving up to make this whole thing happen at the right time. Equals 0.9 meters per second. And then it would take that long. Show your reason. No, that's it. So I guess maybe, let's see, what must be changed about how this starts off? Explain to show that your answer does indeed cause the block structure out of 10 seconds. Maybe just do it wrong or something. I'm not sure. Yes. So that was counted when we did this, right? It's still hooked up to all the ropes and everything, so it's still reduced. But on the way up, it might be different. Let's see, did I look at the solution to this problem? Let's see. Yeah, no, it would still be weird because this mass would be pulling it down. Okay, we have the final, let's see, I have a rotational problem. That's what we've been wanting to think about, is the rotational problem.